Yeah, good morning all of you. Welcome to the course on microsystems and MEMS. So, MEMS the full name is Micro-electro-mechanical-systems, and this is a very emerging area today, and lot of work is going on around the globe on MEMS and microsystems, and it has got enormous applications. Today we will highlight the basic applications and some of the introduction on MEMS and microsystems. Now, the MEMS topic or microsystem is an offshoot of the microelectronics, and so to start the course on MEMS and microsystems, we will start from microelectronics, and let us look back little bit into the backs of the present MEMS, which is microelectronics, and we will look into the history on microelectronics. So, this particular figure you can see the three scientists who are the Bardeen, Brattain and Shockley from the Bell laboratories, and you know these three scientists first discovered the point contact transistors, which is in 1947, and for that discovery they got Nobel Prize in 1956, and that was the first time Nobel Prize was awarded for an engineering device. You know, Nobel Prize is not given for any engineering branch, it is given on basic science, physics, chemistry, mathematics, etc. But here the Nobel Prize was given in physics for an engineering device. Later on, these three scientists developed a technique by which silicon can be oxidized, and oxidation demonstrated by them in 1953 at Bell Lab, and because of that demonstration of oxidation from silicon, basically the people started thinking, so why can we not make the transistor on silicon monolithically. The first invention on transistor was a point contact, that is a discrete. Basically they combined three pieces of silicon, N, P, N or something like that, and then they took contact on each point and they got the transistor action. And this figure you can see is a Jack Kilby, and he invented integrated circuit in 1958. You can see here, so that is the US patent, and which was submitted in February 6, 1959, and this was in September 1958 the patent was written, and that was the first monolithic integrated circuit. You can see the picture here, and this gentleman is a Jack Kilby, and he got again Nobel Prize for this particular device in 2000, year 2000. So, from that time onwards, people are not seeing back and they are proceeding forward, particularly in the context of miniaturization of different components and making the integrated circuits. Now, this picture you can see, which is the MOS transistor, which contains over 1 million MOS transistors, and that is early 1990s. Now, if you look back to compare the revolution in the integration of the components, so you have to go back to the first transistor, which is also monolithic, and that was made in 1960s. 4 BJTs and several resistors are connected together with some metal line. You can see there, this is a metal contact, this is a metal bond pad, here is another metal bond pad, and the 4 transistors and several resistances were integrated to get some function of to get some circuit. Now, after that, if we see what is the status and what are the trends of silicon ICs, we have to see this particular figure where this has been obtained from CR roadmap, and here in one side you can see the minimum feature size of the transistor starting from 1970 to 2020, and on the other side you can see the number of transistors per DRAM chip. So, now look at this figure here in 1980, where this minimum feature size was nearly say 2000 nanometer, and then if you go at present, this is the present line 2004, and there you can see the feature size is nearly 100 nanometer. So, on the other side, the DRAM chip, which is basically always cited the integration level, and that integration level starting from the 4 kilobit, this is 4 kilobit DRAM, which has been which has come in 1970, and later on you can see from 4 kilobit to 64 kilobit, then 1 megabit, then 16 megabit, so and so on. At present 256 megabit DRAM, where this is nearly in 1998 or 99 it came, and their transistor count you can see here is a 1 10 to the power 9. So, that means is nearly people are thinking at the moment. So, transistor level has come of the order of 10 to the power 10 transistors per DRAM chip. And now, this if you here is one limit by 2010 and 2012, you can see the number of neurons in the human brain in 15 centimeters cube is nearly 10 to the power 11. 11 is the total number of the neuron cells, and people are speculating that by that time the number of transistors per IC or DRAM chip it will achieve in that level. So, now this is another picture you can see, which is basically Moore's law, and that gives you the scaling of the CMOS. That means year to year how the integration is taking place. You can see from here the modern CMOS in 1980, which is nearly 1 micron technology, and then at present in 2004 the transistor size has come down to 90 nanometer only. And here basically a roadmap is given by a international organization, and that is the semiconductor roadmap they call it, and last 34 years the scaling history is such that every generation feature size shrinks by 70%. What do you mean by the generation? The generation basically on an average every 2.9 years they speculate something, they foresee something, and after that on that particular year again, depending on the progress of the design and progress of the technology, they again look want to just conclude something. So, the next 2 years what will happen. So, that is basically the roadmap. Earlier this generation is nearly 2.9 years, but later on the progress is so fast that has been changed to 2 years. Recently every 2 years they are speculating something, and before that target achieved, that time target achieved, they got something else, much more progress has been done. Now, basically the scaling of the CMOS, if you can see that the beginning of the submicron era is started nearly say mid of 85, mid of 80s, that is 1985 nearly in that. After that deep UV lithography, then 90 nanometer in 2004. So, if you continue in this fashion, so presumably by 2020 they will come to a limit, and that limit of scaling, that means there the problem is the lithography alignment or lithography, which will be the source of lithography. So, optical lithography is a commercial technique, you know, there the ultraviolet, then they proceed to UV, deep UV, and then after deep UV there are certain other lithography techniques which are basically X-ray or ion beam lithography, but those are not commercially viable. The people want to stick on optical lithography itself. So, that is why optical lithography creates some problem after the 90s nanometer and below. So, lot of innovation and techniques people are using in the optical lithography, so that they can get the feature size below these 90 or now at present 60 or 65 nanometer people are working on. But now the silicon microelectronics, basically if you see, that is this is a silicon wafer, is a 100 crystal orientation wafer. Now, at present the standard size of the silicon wafer in industry is nearly 12 inches, and normally in some cases the 4 inch or 6 inch and 8 inch wafers are also used in some of the small fabs, but big fabs they are working on 8 to 12 inches. Now, you know the lot of circuits are made on silicon wafer, and then a individual single chip, and that is of the order of 2 centimeter square. I am talking about a chip size, larger chip size which you can make nowadays. This is of the order of 2 centimeter square. That does not mean that feature size is also very large. Feature size is very small, and if you can get the larger die size, that is another achievement. Feature size goes down and the die, this is known as the die size goes up. So, that is the challenge of the technology. Now, the currently what I just mentioned few minutes back, that the number of transistors charged per chip has exceeded the 1000 million. So, this is heading towards the billion, and projection in 2014 is 20 billion transistors per chip. So, that is the projection at the moment. Now, here is another the CR the diagram, where you can see the feature size if you goes down. So, if you look into the integrated circuit history, so then the below this is a 0.1 micrometer, and this is 10 nanometer range. This is the one transition 0.1 to 10 nanometer, and then another transition level is 10 nanometer to 1 nanometer. So, 1 nanometer means this transition is very important. People this is basically the quantum devices. Now, you know the lattice the constant of silicon is nearly 3 or 4 or 5 nanometer. Now, if you go into 10 nanometer, that means few 2 or 3 atomic diameter is like that. So, that means that the few monolayers of silicon within that, if you go into this region, you have to make the devices. So, there the normal physics of the transistor may not be valid, and you have to go into the quantum mechanical analysis, and those are basically the quantum devices. And below that is the atomic dimension, and the atomic dimension level, when you make the transistors, lot of other problems will come into the picture. And then here is another table which shows that the trend of the feature size as well as the wiring levels, the mass count and supply voltage, that all this figure tells that is in 1997, where the supply voltage is nearly 2 volts, and in 2003 it is 1.2 volts, and people are looking for the circuits and devices which will work in 1 volt at the, and in 2012 is a 0.5 to 0.6 volt. So, you see how the feature size goes down, at the same time the chip size is going up. As just now I mentioned, to 80 millimeter square. So, they are speculating 2012 it will be 1580 millimeter square, and number of transistors is in that regime it is 1.4 billion, and that is wiring level. That means, in at the present all the microprocessor chips, the 7 or 8 level of metallization is being done there, you know, and if the number of levels is more, the technology is getting much more complicated, and obviously it the yield is another important point, which is another yardstick. So, how your technology is good, how it is commercially viable, etc. So, yield should be very good. So, for that, if you number of levels of metallization increases, so then automatically you have to compromise with some yield, but you have to make a compromise and good yield, at the same time number of wiring level increases, that is the motto and target, and mass count is going to increase if the levels are more. So, in interlevel metal you have to have a dielectric layer, then some metal pattern, then again another dielectric layer. So, automatically mask level will also increase. So, that was the present scenario. Now, the size what I am discussing does matters. How you can see this figure here. So, this is the area of the micro machining and this nano machining. So, another word you are coming across now, this is machining. So, machining, the terminology initially it was in mechanical engineering, people they used to coin that term machining, that means from a huge bulk steel or any of the metal beam, they used to machine it to get small miniature structures. But later on the machining is used in microelectronics laboratory also to fabricate the MEMS devices. Now, here you can see the 1 meter, that is the elephant, and then is gone down to 0.1. So, that is the chip size is, you say, this is the area where 0.01 meter to 1 centimeter, in that area you can get the IC chip. Then this is the size of 1 millimeter, the grain of sand, and then biological cell comes nearly 0.01 millimeter to 10 micrometer, and then comes 1 micrometer, which is the smallest feature size 0.35 micrometer, is sometimes back maybe in 1996, 97 there, that is that level is micro. Now, if you go beyond that 0.1 micrometer below, that is enter into the nano area, and there you can, some of the examples are shown, the atomic lettering using the scanning tunneling microscope, this is 1 nanometer of the order of 10 angstrom the feature size, then DNA is of the order of 2 nanometer wide, that is the size. On the other hand, if you see the machining, so this is the micro machine gear, which is nearly 100 micrometer, then this is the dust particle size, you can compare with that, that is a 1 to 5 micrometer, and these are some quantum electronic structures. The width of these structures is nearly 200 angstrom, and the atomic level 1 to 4 angstrom. So, that means the size does matters, because with the reduction of the size and minimum feature size, all the technology is going to change, at the same time the equipments are going to change, and if you go below say 1 nanometer level, then physics of devices is going to change. So, now if you look here, the size also on the scale, that is a bottoms up and here is tops down. So, both are shown here. There are few areas, this area is basically plant and animal cell, and this is the bacteria size is a 1 micrometer to 10 micrometer, and 10 to 100 micrometer is a plant and animal cell. This is the area where basically the MEMS are made. And now, if you go beyond that, that is not microelectronics, that is basically coming nanoscales or nanoelectronics, their size comes below the 100 nanometer to say here is say 1 nanometer, and below 1 nanometer the different area. So, 100 nanometer to 1 nanometer, that the size of the virus, proteins, and the helical turn of the DNA, and this is the minimum feature size of MOS transistor in 2004, you can see here. So, people are working, so 10 nanometer or 15 nanometer level, obviously that is the nanoscale further nano, and this is 100 nanometer MOS transistor, you can see the gate dielectric is from here to here. So, now this science of miniaturization, with that you can see in case of machine how the size is going to reduce, and here the size is basically is accelerometer, and here is a MEMS accelerometer. Now, side by side if you compare, you see the initially the conventional, the accelerometer, the mass was the nearly 1.5 kilo, more than that, and its size is 15 centimeter by 8 by 5 centimeter, and it requires power of the order of 35 watt. And on the other side you can see the if a MEMS accelerometer if you use now, so that mass is only 10 grams. So, instead of 1587 it has reduced to 10 gram, and size is very small compared to this. Power instead of 35 watt it is only 1 milliwatt, and cost instead of $20,000 it has come down to only $500. So, at present it is further down, the price is further down, and you can get nearly 10 or 50 or $100 MEMS devices. So, although the microfabrication was originally limited to silicon, now the field is open, people are started using some other materials than silicon, particularly the polymers and ceramics and composite materials are also coming into the picture, and people are using those materials for the MEMS and MEMS devices and microsystem fabrication. Now, why people were sticking at the beginning only on silicon, there are certain reason, because silicon technology is fully mature, and because there is no new research is to be done for the processing of silicon, that is why they do not want to deviate from the silicon. But later on the other material, particularly polymer and organic material, has some other advantage in certain areas. So, they are going to switch from the silicon to other non-conventional materials, also non-silicon materials also for making MEMS. So, now the science of miniaturization, if you look into that, so although lithography has been the current method of defining patterns, many forms of direct write schemes are also being used nowadays, and traditional electroplating, molding are being used in micro domain. This is not used in case of the normal microelectronics, but in case of MEMS we are going to use the electroplating, molding, micro molding, and this Liga, all these are coming into the picture, and all the techniques I will discuss in detail in future classes. And now this is a micro and nano world. If you look here, so you can see is a various the application areas. So, those application areas are basically, one is the say the physical MEMS or physical sensors, which deals with pressure sensors, force, inertial, sound, means these are one area where the MEMS devices are made. Other area is micro optics, optical area, which we call it the MEMS, Micro-electro-mechanical systems. So, there is the optical domain, there are a lot of devices are made using micro machining technology. Then another is a micro probing, there STM and AFM, the AFM components are being made using the MEMS. Others is a microfluidics. Microfluidics is a major application is the biology, and not only the biological application, there are others in flow of gas on flow of fluid in a micro channel. That dynamics is very interesting, and there lot of devices are being made now. This is another area of microfluidics. BioMEMS, lot of work is going on, and one emerging area of research at present, BioMEMS area, and the actuation and motion, that is basically the actuators are also very important. If you want to make a microsystem, what do you need? You need the sensor, you need actuator, and you need the signal conditioning circuits or processing circuits. So, actuator is one part of the microsystem. So, if you look into only the microsensor development, that will not complete the microsystem development. If you want to have some microsystem, you have to see how the actuators can be made, and it can not only made, how it can be integrated with the sensor and also the signal conditioning circuit. So, that is why this is another area of micro nano world. The actuator, how can you make the actuator precisely working actuator is very important, and which is integrable with the microsensors. Now, here now let us look into the MEMS history, and there if you see look and the gentleman is a fine man, you know, and he basically got a Nobel Prize in 1959 and in physics again, and he has a vision, and he that time he declared that there is a plenty of room at the bottom. That means on silicon inside you can make lot of small miniature devices, and that means there are a lot of space available which people are not utilizing. That vision has come true in 1959, that has been basically announced. In 1967, if you look, that transistor basically resonant gate transistors came from Westinghouse. Then in 1989 is another thing, is a basically MEMS device started. This is the picture is basically one micro motor and has been developed in UC Berkeley. And then in 1991 you can see the MEMS devices, which is one digital light processing chip that is used in DLP projector machine. And this 1993, these are the accelerometer. If you see commercial MEMS accelerometers coming from analog devices, ADXL series accelerometers, and there if you look here, that is basically the chip inside, and not only the chip, you can if I enlarge the picture, you will see the signal conditioning circuit is also inside. And then in 2001 commercial optical cross connect and switches has come into the market, that is the MEMS devices, optical MEMS. So, these are basically from 1959 to 2001 the history of MEMS, and at present if you see the the microstructures made out of the silicon and other materials. Some of the structures are shown, the hinge slider, and this is the one gear, this is a pin joint. So, this is all this made using the micro machining technology. Now, there are two things, one is the MEMS and microsensors. Sensors is a very important device nowadays. No system can be made without use of sensor. Lot of sensors are there, any of the microsystem. So, that is basically the difference between sensor and micro is nothing but the physical dimension is very small in case of microsensor and in the range of sub-millimeter level. On the other hand, the MEMS or MEMS micro-electro-mechanical system is a device where microsensors and mechanical parts along with signal processing circuits and are integrated on a small piece of silicon. Sensor in earlier days, sensors and circuits are not integrated on silicon, but if you integrate both the devices, then it is known as the micro-electro-mechanical system. Mechanical means they are basically the mechanical part means actuation part. Actuators will be there as well as the sensor part along with the circuits, that is the MEMS. Now, as the computing power increases, the information systems also move into the physical world. Lot of the application in physical world using the MEMS, and where the MEMS is playing a major role, that is in particular in case of I/O of input output device of any of the information system, and they can sense and create motion, velocity, acceleration they can produce, and at the same time in the optical side these devices can reflect or refract light or radio waves also. And at the moment the pumps and control fluids, gases, reactions, gases and reactions are also done with the help of MEMS devices, and these are integrated any of the information system nowadays. Now, the distinctive feature of the MEMS are threefold. One is miniaturization, second is the multiplicity, and the third is the microelectronics. The miniaturization, already I told you how the size are bringing down and down both sensors and actuators, and they are integrated together. Multiplicity, basically the multiple functions are being made in a system. If you want to have a large machine, large task, so you have to have some small micro machines, and those micro machines are coupled together and integrated together to get best performance on a single chip, that is the multiplicity. And at the same time, the another advantage is that if you are going to integrate, not only integrate, you are also going to fabricate those devices in batch production. That means, if you make many of the devices from the same chip, so automatically cost will be reduced. At the same time, many machines, if you integrate together, they work in parallel. So, the total system, if you can think, then its cost will also reduce. So, that means it is inexpensive. On the other hand, another thing is the microelectronics. It integrates microelectronic control device with sensors and actuators. So, these are the three primary distinct features, namely miniaturization, multiplicity and microelectronics. Now, the basic microfabrication techniques, so are in case of MEMS are two. One is known as as I told you, machining is the key feature of any of the MEMS devices, and there are two kinds of machining. One is known as the bulk micro machining, other is the surface micro machining. So, bulk micro machining, the first picture you can see the bulk silicon is etched to have different kinds of shape. So, depending on the techniques used in fabrication, you can create a membrane, you can create a rectangular hole, or you can create a feature like this. So, here the yellow color piece is basically silicon, and the red color is the passivation layer, and the green color thing here is the etched top layer. So, that means there are techniques used by which the etch can be stopped automatically. That I will discuss in detail in micro machining lecture. And now depending on the size of the opening of the passivation layer, you can get different kind of structure from silicon itself. And in the bottom picture is taken after surface micromachining of silicon. Now here you can see this is one kind of the cantilever, and this in the bottom it is basically vacant, you can see here. So this is a hanging kind of thing, and that whole the structure is on the surface of the on silicon. So that means if you can etch with a controlled manner to remove some of the material, either it is a structural material or it is a sacrificial material, to have different kind of structure at the surface. So that is why it is known as a surface micromachining, and this particular process is fully compatible with the VLSI process, and the VLSI chips can be made on the same silicon along with this the microsensor if you go for surface micromachining technology. Okay. Now, I will just give some of the examples of on the structures. So, those are one structure you can see here. So, this is basically the some of the cantilever beams, different size of the cantilever beams you can made out of silicon, and those are hanging, and below silicon has been etched, and you see this is another kind of structure. The side walls are kept here, side walls are kept, and the bottom is vacant, is removed. So, these are the various kinds of the microstructure which is used in many of the devices. On the other hand, here you can see this is a diaphragm, and this is a one kind of diaphragm. On the diaphragm some devices are made, and this is are the bonding pads, and from where the wires are taken out, and these diaphragms are used for many of the vibrator. In some case of the diaphragm is used, or the membrane is used in case of the sensors like the temperature sensors or IR detectors. So, here is another structure which is silicon membrane at the bottom of the silicon, and this membrane is basically held by 4 cantilevers, and this is one flexure or cantilever, another flexure, and these flexures are positioned in such a fashion the whole membrane is held properly, and this on the membrane either you can make active devices, or also you can make some passive components, or only for actuation also you can use the membrane. This side you can see this is a electrostatic motor. This is another MEMS devices, and that is another challenge people has solved, that is motor which was big size. People earlier they had idea how it can be miniaturized, it is not possible. Now, in the last few years the R&D has gone in such a level. So, a micro motor of the size of say few millimeter by few millimeter you can have, that is basically electrostatic motor, and this is the basically rotor, and this is the stator. In the side this color is stator, this is the rotor. Now, by using the electrostatic field you can just this rotor can be rotated, by just you can maintain a gradient of the field in the stator. So, that because of the electrostatic attraction the rotor can move from one of this the line to another line, and again if the gradient is maintained it will come here, then it will come here. In this way it started rotating, and this sort of the motors are very useful any of the miniature devices, particularly in case of biological applications. These micro motors are used as for microsurgery or knife etc., for removing some of the biological species from the body. So, now other few examples I am showing here, that is a bulk micromachine accelerometer from silicon microstructures. So, here you can see this kind is the bulk thing, this is the bulk, and this is here is some kind of the membrane, and from there some structure has been made. So, this is another is a single chip microphone, and that is the back plate is a gold coated back plate, and here this is the structure basically vibrator, and then the other circuits, because in a microphone the first the acoustic signal is received, and that is converted into electrical signal, and that signal again amplified electron. So, the whole thing can be made out of silicon. The single chip microphone can be made using the MEMS technology. These are the some holes, those holes are basically some the etched pits on silicon that can be also made by using the micro machining technology. Here I showed you earlier one accelerometer chip. Here is another accelerometer from Analog Devices, and here you can see this is basically the acceleration sensor, and this sensor has been enlarged, the picture has been enlarged here, this particular portion you can see these are the some fins are there. So, because of the acceleration, the movements of these cantilevers will be there either and as this is basically the capacitive surface micro machine accelerometer. So, because of the acceleration the capacitance will change, and that capacitance change can induce the change in electrical signal, and that signal can be processed by the circuit which are developed side by side. So, that no further noise will be introduced into the system, at the same time no loss of signal. So, you can get maximum efficiency of that particular chip, and that is the airbag the accelerometer chip, and lot of applications are there in airbag. I will discuss the applications of the microsensor in automobile, then again I will highlight what are the various kinds of the microsensor used in the present day automobile industry. Now, another area is the biological application of the MEMS, and there if you see the devices are many devices are made out of the silicon or the polymer, and those are you can see lab on a chip. This is the lab on a chip, and here basically lab means where the diagnostic is being made. That means you see your blood culture, or you want to have your lipid profile. So, blood sample is taken, and there are a lot of chemicals are made, and then after reaction the reagents are analyzed, reaction byproducts are analyzed. From there they can come to a conclusion the composition of the blood, like cholesterol level, like creatinine level, or the sugar level, etc. So, now in a chip itself, if you have lot of cavities, micro cavities, and each cavity is having some of the reagents. So, then automatically if there are certain channels, a small amount of blood is pushed into a small channel, and then it will flow through the micro channel into the different cavities. The reaction will take place, and their sensors are there to know the different composition, different levels of the blood constituents. So, at the same time using small amount of blood you can have total diagnostic of your blood or lipid profile, your blood you can get it. So, that is known as a laboratory on a chip. And another picture you can see, this is a drug delivery system. So, drug delivery system is automatic drug delivery system. That means in many cases you know particularly in hospital or nursing home, when patient is admitted in the night, if the attendant is not there, if he has severe pain, so he needs some drug for releasing his pain. So, if no attendance is available, then there is a lot of chaos and problem. So, if a small chip has been developed, so if you fix this chip on his hand, so automatically some pain is there, some painkiller in a liquid form would be automatically injected into the body. So, there is no continuous monitoring is not required, the chip itself is taken care of. On the other hand, the lot of people is having blood sugar. So, when to put the insulin into his body, that can be diagnosed by a particular chip, and the chip continuously monitoring the health and the sugar level of a body, and then whenever required the insulin is injected into the body. So, that is the drug delivery system. That means there you have to have certain diagnostic feature as well as delivery feature. So, it is a very intelligent module or chip, and that is coming nowadays in many of the advanced hospitals or in patient take care of places. So, there this drug delivery system is another solution in place of continuous monitoring by some sisters or doctors. So, DNA analyzer, lot of the DNA research is taking place gene research is taking place, and there also this the MEMS is playing a major role. And application wise, others are the food testing, clinical diagnostic, as I mentioned, environment and biodefense. These are other application area. These are the some of the pictures of the bio-MEMS devices. Now, the advantage of the MEMS are manifold, and particularly these MEMS devices nowadays which are coming are IC compatible. As I mentioned, if it is IC compatible, its performance is very good, and miniaturization has got threefold advantage. Not only size is small, it is a rugged, and at the same time if you reduce the size, then power consumption are also low. That is another demand of the day. So, whatever the system or chip you made it, power consumption should be low as minimum as possible, because everybody wants the system should be battery driven, and battery driven means the voltage level if the whole system should work 1 volt or 2 volt or 1.5 volt in that range. So, for that you need the power consumption should be less, so that your life of the battery will be higher. So, you have to make innovation in circuits, so that low power, low voltage, low power circuits are added into the feature. At the same time, you have to have the device, miniature device whose power consumption will be extremely small. And the third one is a batch fabrication. Batch fabrication means the low cost. So, automatically is obvious, if the same batch you can fabricate millions of devices. So, cost per chip will be reduced drastically. So, these are the three major advantage. Now, the impact on engineering, the MEMS devices, what are its impacts on engineering? So, it is basically a driver for multiple and mixed technology integration. What is mixed technology? Multiple technology. That means, here technology is not only electronic technology. So, here they are combining materials technology, electronic technology and mechanical, because as I told you, the MEMS means motion is involved, that means the mechanical movement is involved. So, lot of mechanical engineering applications are integrated with electronic application. That means, technology is a mechanical technology, materials technology and electronic technology, all are integrated together. So, that is a driver for integration of those, and orders of magnitude increase in the number of sensors and actuators. So, that is another potential impact. So, and the third one is the beneficiary of and driver for information systems. So, in a present information age, so MEMS and microsystems are driver for taking the information technology ahead manifold in forward direction. So, others are the VLSI as a design and synthesis approach for electromechanics. So, it is electromechanics. Okay. So, these are the different impacts on engineering. Now, the again multiple and mixed technology integration you require in this particular area interdisciplinary research, because VLSI is basically the research area where only electronics and electrical engineering people are involved. But here in the MEMS or microsystem technology, the interdisciplinary research and people from different disciplines are required. Physics, chemistry is also, people are also involved. Lot of etching here is a micro machining or etching, whether it is a liquid or gas etching, lot of knowledge of chemistry of the materials and devices and gases are also necessary. So, knowledge of chemistry is very much involved here, physics is everywhere, material research is required. So, interdisciplinary team is required for R&D on MEMS and microsystems. So, MEMS will counter the technology for narrow specialization. So, people are working narrowly in different aspects. So, in device simulation design, a group of electronic or electrical engineering people are working only, material research, material science people are working. Now, this narrow specialization people have to come out of that narrow specialization, and one has to see how we can different knowledge can be coupled together to have a good system which improves the information, which take forward the information system or information age. Teams that best integrate multiple disciplines will be best positioned for future opportunities, and new materials are also necessary nowadays because of different applications. What are those materials? As I mentioned, that polymer is coming in a big way in MEMS devices, because lot of polymer materials are biocompatible. On the other hand, silicon devices are not always biocompatible. So, that is why the lot of emphasis is given nowadays in polymer MEMS research, and the lot of composite and ceramic materials are also coming into the picture. And now for making the MEMS devices, first you have to design the MEMS devices. For design, earlier we used to get some device some software tools for the VLSI devices. MEMS device tools, simulation tools were not available, but gradually the MEMS device simulation tools or MEMS design tools are available, and those are namely MEMS CAD or Coventerware from Coventer Incorporated USA. Another is the MEMS Pro, MEMS CAF from France, and IntelliSense from Corning USA. These are the three major simulation tools for MEMS design. And other than this, there are other device not device, the design tools are used. Those are the ANSYS are also being used nowadays, because ANSYS is a basically finite element analysis simulation tool, and is a MEMS and microstructures as not regular structures. There are a lot of irregularities is there. For analysis or simulation of those structures, you have to go for numerical techniques. Okay. And for numerical techniques, either finite difference or finite element tools are very much useful, and there based on those finite element or finite difference method, these softwares are developed. And these are some of the structures obtained from the simulation tools, and you can the mechanical analysis, thermomechanical analysis, electrothermal analysis, all analysis can be made using those software. Now, I will spend sometimes on the players on the MEMS and microsystem. Some key players around the globe who are working on this particular area at the same time who are producing commercial MEMS devices. So, namely the first is coming into this area is Analog Device Company. They are concentrated on integrated accelerometers made by surface and micro machining technology. Their major product is micro-accelerometers. Another player is the Motorola. They concentrated on pressure sensor made by bulk micro machining technology. Others are Delco GM, again the pressure sensors and accelerometers made by bulk micro machining technology. The other one is Lucas Nova Sensors. They concentrate on pressure sensors and accelerometers, and Texas Instruments integrated micromirror projection display made by surface micro machining technology. The DLP projector basic technology is coming from the TI. So, these are the major players. Now, worldwide activities, if you look, you can see this picture here. So, you see the major activities going on around the globe in I am just from different countries, particularly you can see USA and Japan, they are far ahead from other countries, and here the blue color represent the companies, number of companies who are involved in MEMS activities, and this color is basically universities or research laboratories involved in R&D on MEMS. So, you can see here the Germany, UK, France, Switzerland, Sweden, Netherlands and Korea, those countries are involved, but industrial or major players in industry are basically coming from two countries which are USA and Germany. And in the Asia, you can see the other than Japan, Korea is also little bit involved on the MEMS and microsystem R&D as well as the production level. So, in a major players are from Europe, particularly Germany, UK, France, Switzerland and Sweden, Netherlands, there the major R&D locations are there. And now at the end I will give you some of the information or resource informations. So, those are very important as we continue this course. So, you need some information for further study, and some of the journals which deals with MEMS papers or MEMS research activities are published. Those are Sensors and Actuators ABC, IEEE ASME J, Journal of Micro-electro-mechanical-systems IEEE journal, Journal of Micro-mechanics and Micro-engineering. These journals are focused only on MEMS, biomedical micro devices, BioMEMS, lot of papers are coming there, and the related journals where not only MEMS, other devices and VLSI papers are also available. Those are IEEE Electron Device Letters, IEEE Transactions on ED, Journal of ECS, Journal of Vacuum Science Technology, Proceedings SPE. So, these are the journals, and now I will give some of the conference regularly organizing on MEMS and microsensors and microsystems. There are solid state sensors and actuator workshop every even year is taking place. International conference on solid state sensors and actuators every odd year is taking place. MEMS workshop every year is annual event. Micro TAS even year it is in Europe, this conference. Eurosensors it is also every year. Many other journals and conferences now have MEMS section. Okay. Now, I will give some of the books which, which are important for further study. Those are MEMS and MOEMS technology and application by Rai Chaudhary and is a SPE publication. Micro-mechanical systems principal cell technology, the Fukuda and MEMS from Elsevier. Microsensors, MEMS and smart devices, the Gardner and Barden, that is again John Wiley publication in 2001 it came. This is a very good book and deals with all aspects of microsensors and MEMS, this Gardner and the Barden. And other than these three books, there are other books available, and those are the Microsystem Design by Centuria, RM MEMS and their application by again Barden, and Fundamentals of Microfabrication Marx J. Maddow, this is also CRC Press book. Semiconductor Sensors by SMZ is also John Wiley publication, and Silicon Micromachining by the Eloin Spock and Janssen is a Cambridge University Press. So, these are few books which are available nowadays in print, and you can have some of the books in our library also. You can borrow those books for further study. And other than these journals and books, lot of websites are available nowadays, and I will give you some of the website addresses also, where you can have lot of information on MEMS research as well as for the present developments of the MEMS, and that those websites are very important. You can just open this website and you can see what progress is going on. There are certain websites, MEMS talk website, where you have some queries, you can post that query, and in the future you can get answer of those queries also. And like all other subject, MEMS books are not plenty. I just mentioned few books, maybe 10, 20, 10, 15 books are only available, and out of those books few are available in the library, others are not available. So, I would request you to find some of the textbooks and go through that, so for further study, and advanced research you can get from website and from the journals. Thank you very much. So, in my last lecture I have introduced the course MEMS and Microsystems. So, by now you know that in MEMS and Microsystems one of the important block is a sensor block, and today's lecture I will highlight the sensor and I will introduce sensor, then we will go to the microsensor and different aspects of sensor, its specification required and its technological aspects. All these things I will discuss in today's lecture. And sensor is a very important device, and now with in microsystem we use microsensors, and I will discuss what is microsensor, and in particular in MEMS or microsystem we normally use semiconductor sensors. And again, why semiconductor sensors? Because semiconductor materials are used in many ICs and VLSI. So, if I can make the sensor out of the semiconductor material, then it will be easy for us to integrate both the sensor part and circuit part together, and that is why a lot of sensors are coming out making use of semiconductor materials. And in the first, let us see what sensor means. And sensor basically is a word, is a coming from a Latin word sentire, and that means to perceive, that is derived from Latin word sentire, and lot of definitions are given for sensors. Basically it gives information about the physical and chemical signals which could not otherwise be directly perceived by our senses, or other parameters which you have to take into account when you are selecting or designing a particular sensor. Repeatability means ability of a sensor to reproduce output readings under identical condition of the measurer, that is repeatability. Same conditions you are applying, the output of the sensor should be same. If it is not same, it is not repeatable, and repeatability may lose because of different problems in your design, different problems you are choosing of materials of the sensor, and different problems of your environment condition also. Okay. And the stability is another important aspect, and that is ability of a sensor to maintain its performance characteristics for a certain period of time. So, that means how long your sensor is performing well, that is the stability. Okay. So, with this I gave an introduction to the microsensors, and something I will continue on this topic in the next lecture also, and then I will discuss on the evolution of these MEMS sensors as well as market survey. Okay. Thank you. Let me stop here.